Hello, hello. How are we all today?
Tired.
Surprise, surprise. I feel like we're doing more work now than we were when we were at school.
I feel that too.
Hey, it could just be that I'm trying to deal with children home, but that's by the by. Okay. I am really curious as to how you guys are going on the capacitor project. All right, well, you have time now. What can we do right now? In the next half hour, what can we do? Watch the video. What is something that you can be doing in the next 10, 15 minutes to get started? Seriously, eat an orange? I do. Okay. What sort of work, Weston? I'd like to see you try and make a capacitor. Can I have at least an idea of what you can do?
Look for materials.
Great. What sort of materials can you look for?
I'm not sure. I haven't finished watching the video.
What?
What is it made of again? It's made of some sort of like conductive and then some sort of like what's it?
Dielectric.
Yeah.
All right. I guess if you're already on here, I'll give you the brief skinny on what a.
It's like a good orange edging.
It's very nice, actually. So what you should have is you should have a battery. Why is that in straight lines? What you should have is you'd have a battery of some sort that has a. Adu.
Wow.
Bless
Okay.
you.
Bless you.
Okay. Thank you. What you want is you want to have some sort of circuit. We know that this end here is the plus end of the battery, and somewhere along here is you want to have a capacitor. I think that's roughly the symbol for a capacitor. And you're absolutely right. In between the two conductors, you want to have some sort of layer there. So that's basically what you want. You probably want to figure out if your connection works, making sure that the thing is there. So you have some sort of that's a horrible. You want to have some sort of light attached here somewhere. You want to have that in there somewhere, okay? Whether that be a diode or something. But this is where you're interested in. Good grief. What you want is you want two conductors thinly separated by Did Yejin give you that orange? And how?
What?
Lydia has
sharing
an
with
orange
me.
now. How did? Sorry, I'm getting distracted.
Magic.
Do. So you want?
The bonds of friendship can go across country barriers.
She handed it to me.
So what you want is you want two conductors, and it's it's much easier to have these as either flat plates or you have very thin sheets that you can then roll up. The reason why you would like to have something that's a thin sheet is so that you can have, instead of having two capacitor plates that are this sized next to each other with a dielectric in between, what you can do is you can put them together like that, and then you just roll them up, and they become much, much smaller. That's just a space-saving thing. You don't actually have to do it that way, but you could have a capacitor this shape. It's much, much smaller. One of the reasons why you find capacitors in these little tube-like things. So what you could do is you get two conductors. What conductors do you have around you that are kind of flat plates so that they will give you that nice, just a second, it's a positive field. So if it's positive there, that'll be positive there, which means that your line of electric field will be this way. Okay, it gives you that nice straight field line if they're basically parallel plates. Okay, so that's what you're looking for. Do you have anything that could either be two flat plates or two thin sheets that you can roll together to make what is equivalent of two flat plates? I'm going to go from top to bottom. Melody, do you have anything? Melody?
I was just gonna say tinfoil.
Great, that'll work. What are you going to use as a dielectric?
I'm not sure.
A dielectric will have a higher resistance. Like you can use air. You could potentially use air in between, but there are better dielectrics. Where are we? Where are we? Where are we? Where are we? Come on. Come on. Okay, turn to page 483. You got page 483 open?
Virtually, yeah.
Here are some choices of dielectrics. Air, your volt per meter is 3 million. Paraffin, your volt per meter is 10 million. Polystyrene, your volts per meter is 24 million. Vinyl, your volts per meter is 50 million. Well, here's one that's fairly common. Paper. That's 15 times less conductive than air. Do you think you might be able to find a consistently thin piece of paper that has like a set thickness?
Yes.
All right. So if you can find a bit of paper and stick it between two bits of tinfoil, that would work.
Can we use like plastic bag and put a tinfoil in it?
Ooh, that's interesting. What's a plastic bag made out of? It's made out of
Plastic.
I was gonna say
really? It's made of low density polyethylene. Let's see if we can find that. Let's find LDPE. LDPE dielectric. Let's try polyethylene, polypropylene. Whoa, it's a whole PDF thing. So let's see what we can find. Let's try to find the volts. No. Does it have? I can't find it. this seems far too complex for me to find where the information is.
Our book calls it dielectric strength. Do you want to try looking that up?
What is the dielectric constant of plastic materials? Let's just go that one. Oh, wow.
Just
Is it just a so foam polyethylene says 2, polypropylene. Dielectric is in the middle. Vacuum 1. Okay, here we go. So fluoropolymers is a 2, polypropylene.
PVC.
I guess it would be similar to that, but it's not that much higher than air. It's only a little bit higher than air.
So PVC is 4.
PVC is 4, but paper is 15.
Oh, should it be high?
Yes. Okay, so if you get to 3 million volts per meter,
Hey,
what will
Mr.
happen
what's
is
dielectric
it will
constant?
air will no longer be a insulator at 3 million volts per meter. It stops being an insulator. It becomes a conductor. So if you have a high enough potential difference, the current will just go through it. Charge will just go boom, straight through. And that's what happens when you get shocked with a Van de Graaff machine or a lightning bolt hits the ground. There is enough potential difference to turn the air into a conductive plasma. Just a second. Maaf, saya lagi Zoom call dengan orang lain. Yes, tolong. Terima kasih. Ya. Okay. Where was I?
Mr. Hindra, what is mica? M-I-C-A. Mica, whatever.
It's like the tops of tables. It's you know the tables at the top.
Isn't that a type of plastic?
You know the tabletops in the lab, that kind of black
Mhm.
ebonite sort of thing. I think
Yeah.
that's mica.
Oh,
I think.
Did you say, Mr. Andrew? Did you say
Can't be
that?
mica because that surface mica is exceedingly brittle. It snaps easily. It can't be it. Yes, you saw.
Did you say the electric constant paper is 15?
According to page 483,
It says it's 3.7.
water is, no, the dielectric constant is 3.7. The dielectric strength is 15. So
But on the screen, it's constant.
Yeah, on screen it's constant.
wow, that's interesting. How can you have a higher dielectric constant and a lower dielectric strength?
Well, what's different between?
I'm actually looking that up now. Okay, so the dielectric constant increases. Dielectric constants increases your capacitance. Okay, so it's different. It just means that it increases the amount. It's got to do with how far the things can move. So it's two different things. I'm so sorry. What you have is you have a. Let's just give a. Let's get a bunch of stamps here. Let's say you have a bunch of. Let's make these protons. Okay, I have a bunch of these protons. I'm going to put two conductive plates here, and then I'm going to give them also a bunch of. Okay, so I've got a bunch of I've got a bunch of electrons here. They should kind of line up. Okay. So with each if you're in a conductor, the electrons can move around as they like. There's a sea of electrons around all the atoms. But in an insulator, those electrons are not free to move. They're stuck. They're stuck with the proton. They can't really leave that proton, but they can move a little bit. Okay?
This isn't in an insulator.
Pardon?
This is in an insulator or a conductor?
This is in an insulator where the electrons are not free to move. However, if I was to, come on, silly machine, don't be silly. If I was to give this, if I was to give up here a positive charge, come on. If I was to give up here a positive charge and I was to give down here a negative charge, what would happen to your, what would happen to your electrons?
Electrons will go to the positive one.
They'll want to move up here.
Mm-hmm.
They'll want to move up here. So that creates it positively charged at the bottom and negatively charged at the top.
Yep.
Now my understanding is the higher that dielectric strength is, the less they move. Either that or it means the more they move. So you can you can build up a greater potential difference on the surface, I think.
So dielectric constant should be lower to make like more like wait, what? I'm confused. What?
Okay. The textbook describes it as follows. Thirdly, it is found experimentally that if a dielectric fills the space between two conductors, it increases the capacitance by a factor K, known as the dielectric constant. It literally says that it increases the capacitance.
So basically, get a good insulator.
I think it means, well,
Wait, is it like opposite?
sorry?
Wait, so you mean we need to get low dielectric constant insulator or high?
You want to get a higher dielectric constant because your capacitance is related to your dielectric constant, and then it's a ratio from your area to the distance between the two.
Oh, okay.
So I've just done that. Capacitance actually, wait. Control Z, thank you. So your capacitance is equal to your dielectric constant multiplied by the area divided by the distance between the two. So if you have two plates that are one square centimeter and a millimeter apart, you would have a capacitance of a certain amount, depending on your dielectric in between. If I have nothing in there, if I have a vacuum, the dielectric constant is just 1. And it's very close to air, which is a 1. Now, I don't know if this means that they're better insulators or less good insulators. I really don't know. There seems to be some connection with the higher the dielectric constant, the more it can withstand, the more energy it takes to actually turn it into a conductor. But I don't think there is a hard and fast rule. It probably has something to do with the electron shells, and I do not know how to explain that at the moment.
So, Mr. Hindro, we want to get something that has a high dielectric strength, right? But if the dielectric strength is too high, then could it not work? Like,
I made a mistake. It's not the dielectric strength. It's the dielectric constant. Paper is 3.7 times higher. So if you had a capacitor with air and a capacitor with paper, if all other things were the same, the capacitor with paper would be 3.7 times, could hold 3.7 times more charge.
Makes sense.
Okay. So my recommendation is use a bit of paper, because your distance will be guaranteed to be almost the same along the whole thing. If you want to use potatoes, it will be difficult because you've got to cut those potatoes really, really thin.
So water is the best to use? Why does it have a dielectric constant but not a dielectric strength?
Okay, your dielectric strength is not there for water. It conducts.
Then why does it have a dielectric constant?
Because you can freeze it.
If you used ice, it would work?
I think so, but
You just
I'm
have to
not
keep
sure.
You'd have
I'm
to
not
keep the
sure
whole system
what
very
exactly the deal with water is.
Do you have any strontium titanate?
Oh yeah, bags.
Okay. Can I pick up some when I pick up my what's it?
My suggestion would just be to get 2 sheets of aluminium and put a bit of paper between them. The paper will also prevent any way that you attach that aluminium to each other from accidentally short-circuiting.
I have a question.
Go ahead.
Go ahead. It's okay.
You first.
Oh, no, it's like kind of different topic. Go ahead. You first. It's okay.
Oh, mine's kind of different topic too. Mr.
Oh,
Hendro,
okay.
when's a good day for me and Weston to come get the things? Wesley.
I think anytime. I'll have to put them up by the satpam post, and you can just pick them up.
Okay.
So I'll grab them from the lab, and I'll put them at the front desk. I mean, at the satpam post.
Like
Have your
tomorrow
little
or
names
what?
on it as well.
Like when?
I can do that within the next 20 minutes, or whenever we're off.
Oh. How about tomorrow?
I can leave it there, and you can pick it up whenever you're ready.
Okay.
Mr. Hendro,
Yes.
what were you talking about vacuum thingy?
Yes.
What were you talking about the vacuum? This vacuum?
Okay.
stays in
A vacuum is the zero condition. It's a condition where they do all your baseline, because you can say, okay, at a vacuum, the area and the distance are the only thing that we can really look at, so that must be the constant one. These are all just ratios.
Oh.
Like if we took water to be the baseline, your dielectric constant would be much, much lower. I mean, I'm not quite sure even what the unit for capacitance and permissivity is. The unit for capacitance, I can't see where it is, but it's in farads. It's measured in a farad. That's interesting. According to this, your charge can also be calculated by your capacitance multiplied by your voltage. So if you knew that, if you could figure out what your voltage was and your capacitance, you could work out the amount of charge. You can work out charge from force as well. Oh goodness, it's so interrelated. That's fascinating. All right. I'm giving you a few moments to go and try and put something together now.
I'm not at house right now.
Okay. Who has aluminium foil?
Me.
Great. Who has a bit of paper?
Hmm,
Who has a battery?
maybe?
A battery, like in
Yeah, maybe.
this thing. This
Yeah.
this thing here. This is called a battery. It holds a charge in a chemical form.
Yeah, I think so. Maybe. I'm saying maybe I
Okay.
am.
Okay, if you can get a battery, you can hook that up, and you don't even need to hook it up via wire. You could use the tinfoil as your wiring.
And then
I've
how do
seen
we find if it works? Oh, we use the multimeter things. That's right.
Sorry?
We use the multimeter thing, right? To find if it works or not.
What you should notice, the way you can test it, is if you put a switch where you can open and close the circuit. So what you'd be doing is you'd be opening and closing the switch. And as you open and close the switch, can you see that the light is flickering or not? Like if you had this disconnected, if you disconnected this from the, if you disconnected this from the circuit, when you start flicking the switch on and off, what will happen is the light will also be flicking on and off. However, if you attach this to a capacitor, what should happen is when you start flicking this on and off, the light, if you do it fast enough, the light should not go off. It's it's a thing that you could stick into light bulbs when you have like it's what's inside a star bulb.
What?
You know the star bulbs, the red boxes we have, voltage stabilizers. I think that's what's inside them. It's just dirty, great big capacitors. And the way they modify the amount of charge it's going is that they actually have the plates move backwards and forwards past each other. So if you want to have more capacitance, you just slide the plates in together, and if you want to have less capacitance, they slide out. I think that's what's inside a star bulb. I'm not actually sure. Do you have a star bulb at home that you could tinker with? No. All right. Just a suggestion. Okay.
Mr. Hindra, do we need a light too then for our circuit?
Do you need a what?
A light.
How would you check it without a light? You could do something else. You might attach it to a speaker. You could attach it to a fan. You could attach it to a motor. Just something so you can see that the power is going off and on and off and on. And then with a capacitor, that drop is not going to be as bad.
Oh, we need wire, right?
Pardon?
We need wire to connect those stuffs together.
You need a conductor. You
whatever.
could get
So
a
what?
wire somehow. You could find a wire. You might want to strip out the inside of one of your like a busted earbud or something. You could make a wire out of tin foil, roll it up. I don't know. It just needs to be a conductor. Please do not use the side of your dad's car.
Okay.
Okay. Okay. Are there any questions?
Wait.
I'm just going to open up something here. I'm just going to do something a little bit quickly here because I want to see that you guys are actually getting something done here because I'm having trouble thinking of how I can get you guys to. Can we post pictures somewhere? If I do.
To share it.
Ah, yes. Can you share on Kakao Talk pictures?
Wait, what picture?
Can you share a picture on Kakao Talk?
Yes, you can.
Please take a picture before Friday's class. I want a picture of your capacitor?
What in the world?
Mr. Mr. Hendra,
Yes.
I just kind of confused capacitor in my understanding as the thing that store electricity, right?
Yes.
Then where, like, according to your picture that you just drew on the screen,
Yeah.
where do we put the capacitor? Like, is
Here,
it
you put it. You
here?
put it in. You put it in parallel.
In here in the well, let me.
This is the capacitor there.
Okay. And the capacitor should be made out of the paper and tin foil and stuff, like put it together.
Isn't it paper and aluminum foil?
Yes. Paper aluminum foil will make your capacitor.
Yeah.
Should it be just one, like, layer of the sheet? I mean, one layer, or? 'Cause
Yeah.
I look
Yeah,
up
yeah.
some blog. I look up some article. It's Korean article. They make a capacitor using plastic bags and tin foil, but they rolled it up.
That's okay as well, because there's the rolling up is just to save space.
Oh, it makes no difference.
And not really. You can leave it
Is it
unrolled.
like-
You can leave it rolled.
As the area is bigger, is it get like store more energy?
I'm going to take two pieces of paper here. I'm going to squish them together, and I'm going to squish one piece of paper in between them. So there is two sheets of paper and a piece of paper in between them. If I get this done right, your area is 1A4, correct?
Mm-hmm.
Okay. This 1A4 is separated by, I think it's 70 GSM. Okay, so there's a set thickness for this piece of paper. I'm going to be careful to make sure the corners are still lined up. Okay, so the corners are not quite lined up. The corners are not quite lined up, but would you say that that area is basically the same?
Yeah.
Is it still an A4 sheet
Yeah.
opposite another A4 sheet with a tiny little bit of gap in between?
Okay, I got it.
Yeah, so it is basically two plates,
Mm-hmm.
but it's just rolled up. That's when you see someone tell you to make a capacitor and roll it up, it's only a space-saving technique.
Okay, I got it.
You want us to roll it up too, or
Sorry?
should we roll ours up too, or
Up
does
to
it not?
you.
Okay.
So how do we check if our capacitor works?
If you flick a switch on and off,
Uh-huh.
if you flick a switch on and off, what should happen is if you have enough capacitance, if it stores enough charge, this light will not go out.
Will not turn out.
No, it won't turn off because you're charging the capacitor. Every time you close that, you charge the capacitor as well. So your electrons are going to come out of here,
Mm-hmm.
and they're going to go back to here, correct?
Mm-hmm.
Okay. As they're going here, and this becomes, you're going to get a bunch of electrons over here and positive charge on the other side. Okay, it's going to be attracted here. Now, when you open this, this is still positively charged. This is going to start flowing through. Does that make sense? And as this is flowing through, the light will still be on. And the light will still be on until it all drains out. It's like a bucket. You have normal current functions like pouring water. If I pour the water and I then stop pouring the water just stops. But if I pour the water into a bucket and the bucket has a little hole at the bottom, I can pour it into the water and I can stop pouring the water. The water inside the bucket's still going to go out, and I pour it in and it starts going up again. Okay?
Oh, so,
that's what
yeah.
a capacitor does. It stores the charge, but it doesn't turn the charge into chemical potential energy the way a battery does. This is why a battery can continue to give out charge as long as it's connected.
So when the battery, when the switch is off, it's not connected. If
Yep.
the capacitor work well, the light still will be on.
For a little bit.
Because, yeah, for a little bit, because the capacitor stores energy.
Yep.
Okay,
It's like
got
when
it.
it's like when you have a device that doesn't really have a battery, like a television, and the lights.
Mhm.
I know that in my house, when the lights go out, mati lampu, the
Mhm.
red dot on the front of the television takes about 3 seconds to go out.
You measure
Okay.
this?
So there's some capacitor inside that.
What force measures the light goes on?
Pardon?
Nothing.
You need to get more capacitance inside your devices there, young miss.
So, Mr. Hendra,
Yep.
why do you need a multimeter for?
You want to check if this worked.
Do we have to like measure the voltage of the
We just like
capacitor?
If the light is still going off and on, what you should notice is that the voltage going across it should be not going so far and wide like this. It should be maybe going like if upright is your maximum voltage, it shouldn't be going bang up, bang up. It should be going bang.
I thought we don't need to use a multimeter if we have a light bulb.
Potentially. I think I gave away how to do it. I think I gave away how to
Okay.
do it without a multimeter. Stop nodding, Lydia.
Okay.
Okay.
Well, you kind of just like drew it out. So yeah, we're gonna do it like that.
Anyway, get me a photograph, send it to Cow Talk of what you've made before Friday.
I will try. Yeah.
You'll do fine, Yejin.
Mr. Hendra, Yuzin's literally in quarantine now. She can't get like out.
Okay.
Okay, I'll try.
Mr. Hendra, Lydia's done.
Lydia, that is not your capacitor thing. You actually need to build one.
Oh wait, you made photographers take a photo, not drawing.
Not take a photograph of the screen. Oh goodness.
No, I mean, you thought you want us to draw or something. Okay.
No, I want you to build the capacitor, photograph it, what you built,
Okay.
and send it in.
That's my English language.
Blueprints for
skill.
one.
What was that, Weston?
I have blueprints for a capacitor.
Get to work.
You want me to show you?
No, I want you to photograph it and show me what you've made.
Give me a second.
I got it.
Hey, you're stealing my blueprints, Weston.
I'm bored. Okay. Okay. What was I supposed to do again? I'm getting multimeters and putting it at the sub pump house. Okay. All right.
Are you putting it at the upper one or the lower one?
I'm gonna put it at the
I'm
lower
gonna
one.
use it
because
for a hat.
that's man. Okay.
All right.
Okay.
I'll see you guys on Friday. Oh goodness, it's stuck. Okay. See you guys Friday.
Okay.
Thank you.
Thank you. Don't die.
Stay healthy.